Also danke vielmals. Mein Name ist Sebastien Dupertuis. Ich arbeite als Senior Applikationsingenieur bei MathWorks in Bern seit 10 Jahren jetzt. Und ich kümmere mich um alles, das hat mit Codegenerierung für Embedded Systems zu tun. Meine Muttersprache ist nicht Deutsch, also ich werde auf Englisch präsentieren, es wird einfacher sein, ich werde weniger Fehler machen. Okay. So, welcome to my talk on getting software into embedded platforms with model-based design. The demo or the use case I'm going to use today is about an electrocardiogram application. Are you familiar with electrocardiogram application? How many of you do know it? Okay, only a little bit. So the idea is that you will put some sensors onto some specific points on the body in order to measure the heart activity. And here the idea is to develop a model in order to do that and then generate code out of this model and deploy it onto an embedded system. So here I have such an embedded system. You can come at our booth downstairs in order to see it as well. So this is how it looks like. So it is made of an STM32 board that is connected to a data acquisition board. And you can see the sensors that are there that you can plug onto the patient, basically. And then once the data are onto the board, then they are processed with the algorithm that has been designed using the model-based design approach. And then you can see the results directly here on the 7.7 display, for example, and the data can be sent over the Ethernet. So like by using UDP or TCP/IP protocol, but also for Internet of Things application if you want to send the data to the cloud. So perhaps I can give you the board and you can pass it around. So here it looks like this. On the right-hand side, you have the patient with the 3 connections for the sensors. And the data are collected on the right-hand side, passed to the board. And then on the left-hand side, you can see with the Ethernet connection, the data that are sent over whatever network. Can be Ethernet or Internet, does not make any change. And then you can see the results directly. So here at the bottom, you can see in blue the raw ECG signal, so ECG for electrocardiogram. And then you can see the intermediate signal in green, for example, and in red one, these are the high-frequency peaks that are detected. Because the goal is that for such a signal, which is made of a low-frequency part and a high-frequency part, the goal is to measure the distance between 2 consecutive high-frequency peaks. You do that over 30 seconds. It's enough. You don't need to do it for 1 minute. You do it for 30 seconds. You compute the average value, and then you multiply it by 2 to have the heart rate in beats per minute. Okay. This is the application. And this is running at 510 hertz, because it's enough to measure value between 0 hertz and 255. Because if your heart rate is higher than 255, it's already very bad. So that's one thing. Good. So this is a video of the application running. It's a short one just to show you the result. So we are collecting data over the patient. You can see that the heart frequency is at 80 beats per minute. And here you can see the different values. So the mean value, the maximal, the minimal, and then the standard deviation. Then you could see that I pressed on the reset button to restart the measurement. And then you can see the second measurement there directly. Here the UDP communication protocol has been used in order to receive the data from the embedded target. And yes, this is how it looks like. So if you want to do a measurement for yourself, please come at our booth for that. Here are the 3 main points to keep in mind for this presentation. So the first one is about being able to use model-based design in order to abstract complexity and to be able to decompose your system into smaller modules. Then the idea is that you can collaborate with several people among the team in order to develop each part of the model. And then also one important point is to be able to find errors early, because as you know, the later you find errors, the most cost expensive they are, indeed. So that's why it is better to find them earlier in the development process and to already simulate what you have created. And then the last one is about being able to generate code for several hardware platforms. And here also one point that we have heard from customers is that most of the time the advantage is not that it can go fast because they can generate code, but it's because they can develop multiple algorithms and test them quickly onto the hardware and see which one is working the best way. So here, one big advantage is to be able to test several algorithms onto several platforms. Regarding testing, as I mentioned, as you can see here, so 60% of the bugs are indeed produced during the specification phase of your development workflow. And then almost all of them are detected at the end while you are doing testing onto the real hardware. And here the idea is really to be able to reduce as much as possible the amount of defects that are detected at the integration phase to reduce cost. And that's where indeed simulation can be very helpful in order to already find errors early in the development process. Good. And also, if you need to certify your products, so here in my case, I'm talking about a medical devices application. In your case, you are perhaps working in other industries, but in several industries, you need also to certify your product or do these kind of things. And if you can already ensure that your system is safe at the very beginning, then it makes things easier to certify your product as well. Okay, regarding the workflow. So here in this case, we are doing what we call a data-driven system design workflow. And first, it starts with the data themselves. So in my case, I have ECG data that I am collecting. And I did some measurement. First, I started with my smartwatch. I collected the data from my smartwatch, sent them to the smartphone, and I already used this data set in order to do some testing. But also, if you want, in some cases, you can generate your data yourself. You can create synthetic data, okay, out of a model. For example, you could imagine if you are doing speech recognition, you could use hidden Markov models in order to generate some specific patterns in the voice, and then you can reuse them directly for testing. Then we have the second phase. So in our case, that was basically to work on the statistics, so to be able to measure the distance between two consecutive peaks. But you can also add the artificial intelligence part to it, where, for example, you will have a look at the features out of the signals that would be relevant. You will extract these features and then train a deep learning model. This is something I have also done in this use case. And what you can do is that you can use MATLAB to directly extract the characteristics. In this case, that was using a wavelet transform. And then you can use them to train your deep learning model. Once the deep learning model has been trained, you can deploy it onto the hardware. Then the third phase is about being able to already simulate your system and test it already during the development phase. And here you see, so as you have seen before, that was the deployment onto the real hardware. But later, I have one video that will show you simulation, where indeed you can directly test your model with real signals or with synthetic signals, as you want. And you can already apply some specific test cases that you would like to use in order to verify your system. So test cases that are derived from your high-level requirements, for example. And finally, we have the last phase where we will reuse the model, because the idea is once you have a model, it's good to be able to do something out of it. Not only use it for simulation, but to reuse it. And here the idea is to reuse it in order to generate code for an embedded target. In my case, I'm generating C and C++ code, but it is also possible to generate code for other platforms like FPGAs, GPUs, and so on. And also, one thing that I've put at the end is regarding the deployment. If you want, you can deploy the intelligence of the algorithm directly onto the embedded system. But if you are doing, for example, a deep learning application and you need a lot of resources, you can also deploy that onto the cloud and just send the raw data to the cloud, and then you will do the hardcore processing onto the cloud itself. So this is the modeling and simulation of the full system. So here, this is a sketch I have done using Visio, just a simple sketch to represent the high-level view of my full system. You can see that on the left-hand side, here we are acquiring the data, and then we go into this pre-processing phase. So here, basically, I'm doing filtering, bandpass filter, low-pass filter, and so on, to shape my signal. And on top, there is one branch in order to do deep learning. So here, I'm just taking the raw signal as it is, and I'm extracting features out of it, go through the neural network, and then I will classify the results. So here we have 4 results, basically. The one that is for normal sinusoidal rhythm, when everything is fine, one for arrhythmia, heart attack, and one for congestive heart failure. So you have these 4 classifications, and this information can be provided to a doctor, for example. And at the bottom, you have the post-processing stage that is directly connected to the pre-processing stage, where we will extract the statistics that we need for our application. In my case, that was the heart rate in beats per minute and also the uncertainty over this heart rate. Yeah, so I think I explained all that. That was clear. Then here it's the modeling and simulation approach where abstraction is key. So you see, with the standard model-based design workflow, we start with the requirements at the very beginning, where indeed you will collect your high-level system requirements. And then you will enter the design phase. And in my case, in the design phase, I'm using Simulink with the type of data set that I have collected, either from the smartwatch or then I collected them from the board directly. And here you can already prepare your model to work, to go onto a specific platform. So here you see, for example, I have STM32. So the board I'm programming is an STM32 one. And there is also an option with such STM microelectronics board is that you can use the embed hardware abstraction layer. That's an abstraction layer they have created for all their hardware so that you can connect your model to whatever board. As long as this board is supporting this embed hardware abstraction layer, you don't need to modify anything, which can be very handy for rapid prototyping, for example, before you go to production with your real application. And then the third phase is the implementation phase, out of which we will generate C code, in this case, either for a microprocessor or for a DSP. And finally, we have the integration phase, where we will indeed connect to third-party tools, like, for example, the compiler, in order to generate the binaries, but also to reuse code replacement libraries, because when we talk about code generation, for example, if I have an IR filter, I do not want especially to generate C code directly from the implementation itself, but reuse subroutines that are already optimized for the processor I would like to use. So this is what is called code replacement libraries, and this is available at the integration phase with the hardware support package for the specific target you would like to program. And on the right-hand side, you have the test and verification phase, where indeed the idea is to be able to compare the result of the test cases you run at the design phase with the result of the test cases you are running onto the real hardware. And here, for example, we are talking about equivalence testing with software in the loop or hardware in the loop or processor in the loop. Have you already heard about these ones? In the loop verification techniques. So that's the idea there. Okay. So now I have a video of the system. So you can see on the left-hand side we have the data acquisition part, and then we have the signal processing part. And after that we have two components in order to send the data. Here you can see the interface, how the signals are indeed exchanged between the components. And if we go inside one of these components, then we can directly implement them using basic blocks. Okay, that's the idea. So here I have implemented two filters, the bandpass and the low-pass filter. And also what I have done is that in the post-processing parts, I will indeed extract the peaks and also find out the statistics in order to find what is the heart rate in beats per minute, but also its uncertainty. So this is what is done there. I will not go too much into details, but that's just to show you. And then you can indeed retrieve the signals that you need, like the mean value, max value, minimum, standard deviation. And also what you can do, you can see that I have emulated the 7-segment display in the upper right corner. So here you can indeed create an emulator in MATLAB directly and connect it to Simulink. And from there I can already simulate if the encoding of the digits is correct for my specific application. And all of this can be done already before going to hardware. And also we have the possibility to directly visualize all the data within the model. So you just need to select which signal of the bus you would like to visualize, and then you can basically run the simulation. Here in my case, I have my 10 signals that I collected from my smartwatch, and then I just run the simulation with the first signal. And then you can see how it looks like. So the 7-segment display is updated, and then you have the raw signal in yellow, the pulse signal in blue, the peak signal in red, and then the distance between the high-frequency peaks. I'm just doing a second measurement, this time with another type of signal where there is an arrhythmia. And you will see that the encoding on the left-hand side is no more A or this round, but it's the symbol B now, in order to detect that indeed this was not a normal sinusoidal rhythm, but an arrhythmia. Then I mentioned regarding code generation, you can go to multiple platforms. So in the first case, we are going to a standard processor. But if you want to do deep learning and AI onto a GPU, this is also possible. You can generate CUDA code directly. And also, it is possible to generate HDL code in order to go onto an FPGA or an SoC. Now, regarding verification and validation, one thing that is possible, I mentioned software in the loop and processor in the loop, but it is also possible to do external mode communication. The idea of external mode is that you will deploy your model onto the target, but still you will be able to monitor everything from within your host desktop. So you will be able to monitor the signals that you want. Also, you will be able to control the peripherals that are onto the target, like, for example, the button switch. You can directly click on the button from a virtual representation of itself, and then you will be able to interact with the hardware directly. In our case, the external mode is done via the XCP communication protocol. So XCP was done in the automotive industry, and we have retaken it because it was very efficient. And here you can set up the communication between the host and the target hardware, either with Ethernet using TCP/IP or using the serial link communication. Otherwise, we have also software and processor in the loop. They are basically the same, except that software in the loop will generate code for one part of your model and keep it onto the host computer. Processor in the loop will do the same, except that it will download the code onto the real target hardware. So here, for example, what we do is that we generate code from the section of the model we would like to test, and then we will create a gateway, create a pill block for processor in the loop, and deploy it onto the target like this. Then we will set up a communication protocol between the target and the host. And this type of verification is non-real-time verification because every bit that is sent through the communication network is indeed verified for integrity. So that's why every bit is verified, and this is not a real-time verification technique. Here I have then the final representation of my system. So the first one I showed you before with the components, the system, and so on, we can call it the logical architecture. This one is more the physical architecture or infrastructure architecture. And in this case, we are really connecting the algorithm to the real hardware peripherals. Like, for example, here, now my inputs are no more signals from MATLAB, but are directly signals from the ADC that is used onto the board itself. Also here I have the reset button, so this time it's not a virtual reset button anymore, but the real one onto the board. You can see it onto the board. It's the red or blue one that you have. So if you want to see this use case, this case study in action, please come at our booth. This is where we are on the floor planning. Okay, I think. There is a comment that should not be there, but okay. So now, when we talk about infrastructure for digitalization, that's the first title I selected. Then there was this proposal for another one, but I'm still not convinced. So let's keep this one. And here the idea is that we have seen over the time that the different companies have defined this infrastructure for digitalization. So on the left-hand side, you can see what we call the smart assets. That's basically the hardware that is passing through to you. That's the edge node, what we call the edge node. And then we have the edge system, where basically you will have, within the same room, you would have several of these edge nodes that are connected to an edge system. And after that, you will connect that to the cloud, to the operational technology system, and finally, to your IT system within the company, for example. So that's the kind of digitalization workflow that we have seen over the time. And then there is indeed two dimensions that we can use in order to measure that. So one is the time, and the second one is when do we have to take a decision based on the data. So this is also a bit linked to predictive maintenance. This is the same kind of things that applies to predictive maintenance, if you are familiar with that. And here you can see that on the left-hand side, that's for hard real-time application. We need to take a decision as soon as possible, but with a rather low amount of data. And for example, I don't know if you have a pump that is processing a lot of flow of liquid or something like that, and then there is a failure. You need to be able to stop this pump as soon as possible. Then in this case, you need to take a decision in a very short amount of time and to stop it. So that would be, for example, the application. Here in our case, we take 30 seconds in order to do a measurement. So then it's, it's linked to what we have here in the edge system. We don't need to, for example, if But it depends. You will tell me, if the patient is doing a heart attack, we have to react very quick. I agree, but in most of the time, the measurement that you will do, everything will be fine. And if you need to send the data to the doctor, it can wait some minutes or some hours before it is sent. And so that's the idea. So we will be more in this area. And then if you want to collect more data in order to take another decision, like for example, when you do weather forecast, you will need a lot of data before being able to do a prediction. So then in this case, you will process the data more onto the operational technology or the IT node. That's the idea. And in our case, what we can do is that we can measure the data and send them to the cloud. And then that's what we would have here. So you see, this is the edge node, the edge system. We collect the data, we send them to the cloud, and then there we can run, for example, our deep learning algorithm. If this one is too heavy to run onto the embedded system, we can run it in the cloud and analyze the shape of the ECG signal later. Sending the data to the cloud has a cost in a way that you cannot send as many data as you want. You have to compress the data, okay? And in our case, the application is running at 510 Hertz. I cannot send 510 data samples of 64-bit precision for double floating point every second to the server, so I will compress the data. And here you can see that the data have been compressed by a factor of 125 or something like that, so it may seem big, but at the end you can see when we compare both signals, the blue one, which is the reference one that was done with double precision, floating point, and so on, and with the red one that was compressed up to a uint 8, then at the end the difference is not that big. Both signals have the same shape, they follow the same rules, so this works pretty well. And then these are the kinds of view that you can get on the cloud. So you see here you have the mean value. So this one is not compressed, that's just one signal, that's fine. It's just one double precision data sample every second, so that's fine. Every dot that you see is one sample that has been sent. Then the same for the deviation, the valid and reset flag, but this one has been compressed. But then when we zoom onto one pulse, it's still nice, and it can be used in your deep learning algorithm onto the cloud. Here is a reminder of our three key takeaways. So first, remember, we have a complex model. We need to decompose it and then reduce the complexity and work in a team. Then it's good to already find errors early and to test your system using simulation early. And finally, if you can test multiple algorithms onto multiple platforms, you get a better idea of what would be the ideal solution in your case. Thank you for your attention. This is a QR code that we have. You can feel free to scan it. And indeed, here you will have the link to the presentation I have done today so that you can download it. You will have the link to some other pages where you have additional information. And last but not least, next week in Bern, on the 14th of June, we will give an event for the medical devices industry. It will be a one-day event. You have the link here as well in order to register for this event. So if you are working in the medical devices industry, please feel free to come. This will be a one-day full event with this demo. I will show it more into details than today. And also we'll have one colleague talking about certification. And we will talk about medical imaging and also AI and deep learning. If you have questions, feel free. Thank you.